Okay, thank you for the introduction. I'm Yue Zheng from Tsinghua University, and I will present our work, WIDA-3 Zero Effort Cross-Domain Gesture Recognition with Wi-Fi. It is collaborated with Yi Zhang, Kun Qian, Guidong Zhang, Professor Yunhao Liu, Chenshu Wu, and Professor Zheng Yang. Human gesture recognition is the co-enabler for a wide range of applications, such as smart home, virtual reality, and security surveillance. And many types of instruments can be used in gesture recognition, such as RF devices, cameras, wearable devices, and ultrasound. And compared with other technologies, wireless devices have some key advantages, including less privacy concern, no requirement of on-body sensors, and more ubiquitous deployment and larger sensing range. Especially Wi-Fi is currently widely deployed. So a number of works have been proposed on Wi-Fi-based passive activity recognition, including ES, COM, and WiMu. In principle, these wireless sensing applications extract other statistical features like strength distribution of the Wi-Fi signals or physical features like powered profiles of Doppler frequency shifts, and then they map the features to human gestures. However, we found that these primitive signal features usually carry environment information, and they are not related to gestures. So primitive signal features cannot be directly used in cross-domain gesture recognition scenarios. That is, we may collect training data and testing data from totally two different domains, like different locations, different orientations, and different environments. To solve the problem of cross-domain recognition, previous work either explore cross-domain generalization ability of the recognition model or virtually generate features for target domains. However, we found that our existing works still require extra training efforts, as they may need to collect data from the new domain or retrain the model when the new domain is added. So here is the question we face. Can we avoid extra data collection or model retraining for cross-domain recognition? A straightforward answer is to move generalization ability downwardly at the lower signal level rather than the upper model level. Specifically, we extract domain-independent features from domain-dependent signals to just reflect the gesture itself. And with such features as input, the recognition model can be trained once and used anywhere. Here is the working flow of our system WIDA-3. It extracts domain-independent feature and then utilizes deep learning techniques, and it finally achieves cross-domain gesture recognition with zero extra training efforts. To achieve it, we meet three challenges. Firstly, how we define the new feature that is domain-independent in theory. What kinds of characteristics it should have is what we need to think about. Secondly, how we extract the feature in practice with the collected Wi-Fi signals. And finally, with the new domain-independent feature as input, how we devise the upper recognition model to fully capture the information contained in the new feature and balance the accuracy and complexity. And solving all three challenges is the main contribution of our paper. Before WIDA-3, we also conduct a series of work on signal modeling and feature extraction with Wi-Fi signals. The first one is WIDA, published at MobiHawk 2017. It models the relationship between a person's walking velocity, location, and Doppler frequency shifts. And it finally pinpoints the person passively with the decimeter level accuracy using two receivers and one transmitter. The second one is WIDA-2, published at MobiSys 2018. WIDA-2 can also localize the moving person at the decimeter level accuracy, but it can only use one single link by jointly estimating time of flight, arrival of angle, and the Doppler frequency shifts of the person. And based on our previous work, we found we usually regard the person as a single point and use torso velocity to model the movements of the human. However, for recognizing complex gestures or activities, we need to take velocities of different body parts into consideration. For example, when the person performs the gesture, the hands, the arms, and the torso may move at different speeds. So for the gesture recognition, we need to define a new feature. Here we list the anticipated properties of signal features for finer-grained tasks. The first is domain independent. It means that it should only capture human actions rather than the domain factors such as location, orientation, or environment, and it should perform consistently across different domains. Second is zero effort. It means that with such feature as input, we don't need to retrain the model for the new domain. The third is finer grained. It means that the new feature should contain multiple signal components that correspond to different body parts. And based on these three principles, we propose the feature Body Coordinate Velocity Profile, shorted as BVP. It is described in Body Coordinate System to remove domain information. The main reason is that same gestures can exhibit different velocity distributions in the global coordinate system if they are performed at different locations or in different orientations. And the transformation is not that difficult if we can know the location of the devices and the location and orientation information of the users, which can be provided by passive tracking systems. And these figures show how the BVP of the gesture push and pull will look like. BVP is a three-dimensional feature. The first two dimensions show how velocity distributes along the x-axis and the y-axis of the body coordinate system. The third dimension is time, as power distributions over physical velocity usually change when the gesture is at different stages. So now we come to the second question: how we can extract BVP in practice with the collected Wi-Fi signals. We utilize Doppler frequency shifts, shortened as DFS, which are widely utilized in previous work for Wi-Fi-based sensing to recover BVP. DFS can be derived from raw signal samples by applying time frequency analysis. And we found that the relation between DFS from a single link and BVP can be modeled using the equation shown in this slide. The assignment matrix AI captures the relation of projection of the BVP on the S-link, and the scaling factor Ci depends on the propagation loss of the reflecting signal. From our previous work WIDAR, we conclude that DFS from one link only capture part of the velocity, that is radial velocity components. So to recover all velocity components, we finally use DFS from multiple links for BVP estimation. However, BVP estimation still faces a problem. The equation system is severely underdetermined because DFS from multiple links still provide much fewer constraints compared with the variables that need to be estimated in BVP. Fortunately, we found that only a few dominant velocity components exist in each single BVP snapshot due to the limited number of major reflecting multipath signals. So we adopt sparse recovery to estimate BVP. We formulate BVP estimation as a zero-norm optimization problem as shown in the slide. The sparsity of BVP is coerced by the zero-norm of BVP. And we use Earth mover's distance in the minimization problem to resolve the unknown scaling factor caused by propagation loss and relieve the quantization error in BVP. Now it's time to show why BVP outperforms other features for cross-domain recognition. Here we show an example video of the gesture push and pull, and we observe CSI, DFS, and BVP in two domains. The user performs the gestures at different locations with different orientations and in different environments. We first observe how CSI varies across different domains. CSI's full name is Channel State Information. It presents channel measurements in the framework of modern OFDM technique. The x-axis of these two figures is time, and the y-axis is CSI amplitude. We can see that CSI of the same gesture can be totally different in two domains. The main reason is that CSI also captures the characteristics of the physical propagation environment and will be strongly influenced by the three domain factors. Now we look at DFS. The x-axis is time and the y-axis is frequency. We can see that DFS will also vary when the domain changes. It is because DFS only captures part of the velocity components, and it depends on user's location and orientation in theory. Finally, let's check BVP. We can see that even if gestures are performed in different domains, BVP varies in the same tendency. So we can draw the conclusion that CSI and DFS are probable to vary across different domains, but BVP still stays consistent. Here we also exhibit BVP examples of different gestures. We can see that BVP is a distinct feature to differentiate different gestures. With BVP as input, we devised the upper recognition model. The model can be mainly divided into two parts. The first part is convolutional neural network. We utilize CNN to extract spatial features from each single BVP snapshot. We choose CNN because at each timestamp, there will be only a few dominant velocity components, as we have mentioned, in each single BVP snapshot. And CNN can achieve both data compression and high-level feature extraction. The second part is the recurrent neural network. Specifically, we use GRU to model temporal dynamics of the whole gesture, and GRU is superior in easier to be trained with less data. And in evaluation part, we will show that with the help of BVP, the simple recognition model is still effective. To evaluate weather 3, we use 7 mini desktops with Linux CSI tool. One is transmitter and the others are receivers. All devices work in the monitor mode and work in the same channel. The transmitter broadcasts packets at the rate of 1000 Hz. And we conduct experiments in 3 scenarios, including classroom, hall, and office. The deployment of the devices can be seen in the right figure. And for each scenario, we pick 5 locations and 5 orientations for users to perform gestures. First, we report the overall accuracy of VIDA 3. We use the data which consists of over 10,000 gesture samples, and 16 users participate in collecting the data set. The 3 figures show the confusion matrices of the 6 gestures for different cross-domain issues. We can see that VIDA 3 achieves consistent high accuracy across different domains. Then we compare VIDA 3 with 3 state-of-the-arts. The results show that VIDA 3 outperforms existing works, and different from these works, VIDA 3 does not require extra training efforts. And we also compare the cross-domain accuracy with different input fed into the upper recognition model. Just as we have shown, BVP outperforms both CSI and DFS, and it is a domain-independent feature. The last figure compares the accuracy with different recognition model. We find that our model, CNN plus RNN, exhibits comparable accuracy with more complex models. Therefore, we believe it is effective with BVP as input. Finally, we studied the impact of training set diversity. A varying number of volunteers from 1 to 7 participated in collecting training data, and the data from another new person is used as the test. We found that the accuracy increases from 74 to 89 when the number of training users varies from 1 to 7. The reasons are twofold. First, there will be more data to train the learning model, and secondly, it will be more likely to reduce the behavior difference between the training persons and the testing persons. As a conclusion, in this work, we propose WIDA-3, a zero-effort cross-domain gesture recognition system. Compared with our previous work, WIDA-3 aims at recognizing complex gestures that involve multiple body parts rather than regarding the person as a single point. And with the domain-independent input BVP and the effective recognition model, the system achieves consistent high recognition accuracy across different domains. The hand gesture dataset and the WIDA series of works can be found in our website. The dataset consists of raw Wi-Fi readings and other features such as DFS and BVP. It can be used directly to test and compare the accuracy, efficiency, and generalization ability of various hand gesture recognition algorithms. Okay, that's all. Thank you.